Welcome to This Explainer. Today, we're diving right in to look under the hood of the modern world. We're talking about databases. We're going to explore exactly how data is organized, connected, and scaled across the internet, literally taking it from the absolute simplest lists all the way up to the massive, globally distributed systems running today's largest apps. Let's get into it.
Okay, let's dive into this. Here's our roadmap for today. 1. From spreadsheets to databases. 2. Anatomy of relational databases. 3. Connecting data with joins. 4. Scaling up with NoSQL. And 5. Rise of distributed SQL.
So, to get started, I want you to imagine a scenario. Let's say you open an online store selling specialty cat accessories. Business is absolutely booming. The cats are happy, orders are flying in left and right, but suddenly you're faced with this massive operational question. How do you actually keep track of thousands of customers, products, and shipping addresses without, totally losing your mind?
Section 1. From spreadsheets to databases.
Now, this right here is what your early business tracking might look like. We've got a customer, Mary Johnson, who bought a cat leash. Later on, she buys 3 more leashes. But she's moved to a bigger place to house all her cats, so her address changes. This brilliantly illustrates the absolute chaos of flat files. Because this data isn't normalized, you end up with massive, disorganized duplication. Think about it. If Mary calls about an order, you're looking at multiple rows with her name, totally contradicting addresses, and no way to know which one is actually current. It's just a logistical nightmare.
Well, the solution to our messy spreadsheet is, of course, a database. Think of a database exactly like moving to a new home. You wouldn't just toss all your loose books, clothes, and electronics straight into the back of a moving truck, right? That would be crazy. Instead, you pack them into specific, organized boxes first. A database is essentially that moving truck, providing structured, dedicated spaces for different types of information so you can easily find exactly what you need when you need it.
Section 2. Anatomy of relational databases.
To really appreciate this, we have to jump back to 1970. An IBM computer scientist named Edgar Codd published this groundbreaking paper proposing the relational model. Basically, it was a way to build cross-linked tables so you only ever have to store a piece of data once. Fast forward to 1979, Oracle brings the first commercial version to market, and throughout the 1980s, these relational databases, powered by the SQL programming language, achieved absolute market dominance.
So how does this model actually fix our cat accessory store? Well, by using a process called normalization. We take that giant spreadsheet and split it into bite-sized tables, starting with a customers table. The anchor here is the primary key. It's a unique identifier. We give Mary Johnson a specific customer ID. Now her name, phone number, and address live in exactly one row, anchored by this primary key. Boom, she is never duplicated again.
But wait, if Mary's information is just sitting in a customer's table, how do we know what she actually bought? Well, that is where the foreign key comes in. We create a totally separate orders table to track purchases. When Mary buys that cat costume, her order record simply includes her customer ID. That ID acts as a foreign key, literally a reference pointing right back to her primary key in the customers table. This is what establishes that relational link.
So, the crucial point is that a relational database operates a lot like a meticulously organized library. The tables are the books, the rows are the individual pages of data, the columns are the headings telling you what data you're even looking at, and the database engine, that's your helpful librarian. When you ask for Mary's orders, the librarian uses database indexes, kind of like the index cards in an old library catalog, to instantly jump to the exact location of the data without having to read every single page in the whole building.
Section 3. Connecting data with joins.
And we actually retrieve this beautifully separated data using a SQL join. Let's step away from the cat store for just a second and look at an attorney analogy. Step 1, you have a calendar table with an appointment for client A. Johnson. That is our primary key. Step 2, you have a separate files table holding legal documents, which contains a foreign key linking back to client A. Johnson. Step 3, when the attorney sits down at their desk, the database executes a join operation. It basically acts as a bridge, retrieving both the appointment details and the case documents, seamlessly assembling them for the user without ever having to duplicate the underlying data. Pretty cool, right? Now, having all these links creates a bit of a new challenge. What happens if you actually delete a record? Like, if we delete client A. Johnson from the calendar, what happens to all their files? To protect data from becoming orphaned, databases use strict rules of referential integrity. You've basically got 3 options. You can set it to Restrict, which flat out blocks you from deleting the client if they still have files. You can use Cascade, which automatically deletes all their files too, or Set Null, which keeps the files but severs the link by erasing the reference to the client. This is what guarantees your data remains perfectly consistent.
I know, if keeping track of all these primary and foreign keys sounds complicated, don't worry. Developers use ERDs, or Entity Relationship Diagrams. An ERD is basically just a visual map of your database. It translates those complex tables and relationship lines into a simple diagram that makes it incredibly easy to spot structural errors. And even better, modern tools can take an ERD diagram and automatically translate your visual concept straight into database code.
Section 4, Scaling Up with NoSQL. Now, yes, relational databases are amazing, but they were built for an era before massive internet scale.
Think about the number one. Traditional SQL databases were architected around one core assumption. They would run on exactly one single machine. And hey, that worked perfectly in the 1980s and 90s. But when the internet boom hit, creating massive applications with literally billions of global users, the single server model just broke down. You simply couldn't buy a computer big enough to handle the sheer weight of modern network traffic. So to handle this massive new internet scale, developers had to make compromises, and that led to NoSQL databases. On one side, you have relational databases offering rigid tables, the SQL language, and strict guarantees that your data is perfectly accurate. On the other side, NoSQL throws out those tables in favor of flexible key-value pairs or JSON documents. By sacrificing those strict relational guarantees and complex joins, NoSQL databases could easily be spread across massive clusters of separate servers.
During the late 2000s, this flexibility absolutely saved the day. Massive workloads from millions of networked users were accommodated by brilliant NoSQL systems like Cassandra, MongoDB, and Redis. They scaled beautifully across multiple nodes and tolerated server failures with minimal disruption. But developers really missed the safety and structure of their old relational tables. Which brings us to Section 5, Rise of Distributed SQL.
Let's move to and see how this builds. After the NoSQL boom of the 2000s, Google engineers realized they needed that relational safety, but at a global scale. So in 2012, Google published the famous Spanner paper, outlining an entirely new architecture. This birthed what we now know as distributed SQL, which, sitting here in 2026, acts as the absolute modern standard for cloud database scaling.
Now, to be considered a true distributed SQL database, there are 5 mandatory conditions that must be met. It must effortlessly scale by just adding new nodes. It must maintain strict consistency so your data is never wrong. It requires resiliency to survive hardware failures. It must offer full SQL support for things like complex joins. And finally, it needs georeplication, meaning the data can be seamlessly distributed across multiple regions all over the world.
By hitting those 5 conditions, distributed SQL basically delivers the holy grail of data management. Developers no longer have to choose. They get the strict, safe, relational transactional guarantees of the 1980s combined flawlessly with the massive multi-server global scale of the NoSQL era. It really is the best of both worlds.
So, we've gone from messy, redundant spreadsheets to single server tables, out to sprawling NoSQL clusters, and finally to globally distributed SQL systems that power today's world. But you know, technology never stops moving. So I'll leave you with this question to ponder. As our cloud environments grow to truly unprecedented, unimaginable sizes, how will your data architecture need to evolve next? Think about it. Thank you so much for joining me on this explainer. Keep learning, and I'll catch you next time.